Every second, trillions of photons pass through your body. Some arrive from the sun, some were emitted by distant stars, some bounced off the walls around you only fractions of a second ago. Others may have spent millions, or even billions of years traveling through space before finally reaching Earth. Every one of those photons carries energy, not a tiny amount of abstract energy, real energy, physical energy, the kind capable of heating objects, powering chemical reactions, moving electrons, and allowing life itself to exist. Without photons carrying energy across space, Earth would be a frozen world drifting through darkness. Yet hidden inside this familiar fact is a surprisingly difficult question. Where does a photon actually get its energy? At first, the answer seems obvious. The sun, a star, an atom, a laser, a light bulb. Something emitted it. Problem solved. But the moment we look closer, the mystery returns. Imagine a photon leaving the surface of the sun. The instant it begins its journey, it already possesses a precise amount of energy. Not approximately, not roughly, exactly. Physics can calculate that energy with extraordinary accuracy. And somehow, before the photon even begins traveling, nature has already decided exactly how much energy it will carry. Why? Where did that energy come from? And perhaps most importantly, how did the photon acquire it in the first place? Nature follows a strict rule. Energy cannot simply appear from nowhere. Whenever energy shows up somewhere, it must have come from somewhere else. A moving baseball gained energy because something accelerated it. A battery powers a flashlight because chemical energy was stored inside the battery beforehand. A fire releases heat because chemical bonds are being rearranged. Energy always has a source, always a history, always a cost. Nothing gets energy for free. And that is precisely what makes photons so interesting. Unlike a baseball, a photon cannot gradually speed up. Unlike a battery, it cannot slowly store more energy over time. Unlike a car, it cannot stop at a fuel station and refill. A photon appears already carrying its energy. The moment it is created, the energy is there. Complete. Finished. Ready to travel. It is almost as though the universe creates the photon and simultaneously hands it an exact energy budget. But how does nature know what that budget should be? To answer that question, we need to think about something that seems completely unrelated. A staircase. Imagine standing in front of a staircase. You can stand on the first step, the second, the third, the fourth, but you cannot stand halfway between steps. You cannot place yourself exactly between the third and fourth step and remain suspended there. The structure only allows certain positions. Nature often behaves in a surprisingly similar way. For centuries, physicists assumed that energy worked like a smooth ramp. Any amount should be possible. Half a unit, 1 unit, 1.5 units, 10.7 units. Whatever amount happened to exist. That assumption feels natural because it matches everyday experience. A car can travel at many speeds. A bucket can contain many amounts of water. A room can be warmed by many different temperatures. The universe often appears continuous. Yet when scientists began studying atoms, they discovered something extraordinary. Electrons were not behaving continuously. Instead, they behaved more like people standing on a staircase. Certain energies were allowed. Others were forbidden. An electron could possess one energy or another, but not the energies in between. This was one of the first great clues that reality is stranger than it appears. Inside every atom exists a collection of allowed energy levels. The electron can occupy one level, then another, but it cannot simply exist anywhere it wants. The rules of quantum mechanics restrict the possibilities, and this strange restriction is exactly where photons enter the story. Imagine an electron occupying a high energy state, not physically higher in space, higher in energy. Like a person standing near the top of a staircase, nature prefers stability. Whenever possible, systems tend to move toward lower energy states. A ball rolls downhill. A stretched spring relaxes. Hot objects cool. Again and again, the universe tends to move from higher energy toward lower energy. Electrons are no exception. If an electron drops from a higher energy level to a lower one, something remarkable happens. The missing energy must go somewhere. Remember the rule: energy cannot simply disappear. The universe keeps careful track of it. If the electron loses energy, something else must gain that exact amount. And that something is often a photon. Suddenly, the mystery begins to take shape. The photon is not creating its own energy. The photon is receiving energy that already existed elsewhere. The energy is transferred, not invented, not generated from nothing, transferred. In a sense, every photon is carrying a receipt, a record of an energy change that occurred somewhere in the universe. Whenever a photon is born, there is a story behind it. Something lost energy. Something changed state. Something paid the cost. This idea becomes even more fascinating when we realize that different photons carry different amounts of energy. A red photon carries less energy than a blue photon. A blue photon carries less energy than an ultraviolet photon. A gamma-ray photon can carry millions or billions of times more energy than visible light. Why? The answer is hidden in the energy difference that created the photon. Imagine two staircases. One has steps spaced very close together. The other has steps separated by large gaps. If you step down one level on the first staircase, you lose only a small amount of height. On the second staircase, a single step downward represents a much larger change. Atoms behave similarly. Different energy transitions release different amounts of energy. A small energy difference creates a low energy photon. A large energy difference creates a high energy photon. Nature is not randomly assigning energy to photons. The photon's energy is determined by the transition that created it. The photon becomes a messenger carrying that exact amount away. And this is where things start becoming truly strange. Because unlike many objects in everyday life, a photon cannot carry just any amount of energy. Its energy comes in precise packets, precise quantities, precise chunks. This discovery shocked physicists at the beginning of the 20th century. For generations, light had been understood primarily as a wave. Waves can have different amplitudes, different frequencies, different shapes. Everything seemed smooth and continuous. Then experiments began revealing something unexpected. Light was behaving as though its energy arrived in individual packets. Not a continuous flow, not an infinitely divisible stream. Packets, quanta. The word quantum literally means a discrete amount, a specific quantity, a packet. And the photon became the most famous example. The universe was revealing a hidden rule. Energy itself was not always continuous. Sometimes it arrived in precise chunks that could not be divided any further. A photon is one of those chunks. One packet of electromagnetic energy moving through space. The implications were enormous. Because it meant a photon's energy was not merely a property added afterward. The energy was the photon. The photon and its energy could not really be separated. Asking where a photon gets its energy is almost like asking where a waterfall gets its water. The waterfall is the movement of water. The photon is the packet of energy. The two ideas are deeply intertwined. Yet this realization creates an even bigger mystery. If a photon's energy comes from an electron transition, then where did the electron get that energy? And if the electron received it from somewhere else, where did that energy come from? The deeper we follow the trail, the further back the story extends. Eventually, it reaches stars, nuclear fusion, the early universe, and perhaps the deepest question of all. Why does nature allow energy to exist in these precise quantum packets in the first place? If every photon is a particle of light, then it seems reasonable to assume they should all be the same. After all, a baseball is a baseball. A grain of sand is a grain of sand. A drop of water is a drop of water. The details may vary slightly, but they remain fundamentally the same thing. Photons are different. Two photons can be completely identical in every way except one: their energy. And the difference can be enormous. A red photon carries less energy than a blue photon. A blue photon carries less energy than an ultraviolet photon. A gamma-ray photon can carry billions of times more energy than a photon of visible light. This immediately creates a mystery. If photons are the same kind of particle, Where does this difference come from? Why aren't all photons born with the same amount of energy? Imagine two arrows fired from a bow. One is launched gently. The other is launched with tremendous force. The second arrow carries more energy because someone put more energy into it before it was released. That explanation feels natural. But photons don't work like arrows. A photon cannot be launched slowly and then accelerated later. It cannot gradually gain speed. It cannot decide to move faster. Every photon in the universe travels at exactly the same speed through empty space. The fastest gamma ray ever observed moves at the same speed as a photon of red light. That fact alone is strange, because if they all move at the same speed, where does the extra energy come from? When we think about ordinary objects, more energy usually means more speed. A faster baseball carries more energy. A faster car carries more energy. A faster spacecraft carries more energy. But photons break that pattern completely. A higher energy photon does not move faster. It carries more energy while moving at exactly the same speed. For centuries, this would have sounded impossible. How can two particles move equally fast while carrying different amounts of energy? The answer begins with something we experience every day: color. When you look at a rainbow, it appears as a smooth transition from red to orange, yellow, green, blue, and violet. To our eyes, these seem like different colors. To physics, they are different energies. Every color corresponds to photons carrying a different amount of energy. Red light contains lower energy photons. Blue light contains higher energy photons. Violet light contains even more. In a sense, color is energy made visible. When you look at blue light, you are literally seeing photons that carry more energy than the photons in red light. This raises another question. How does a photon know how much energy it should have? Nature somehow assigns an exact value the instant the photon comes into existence. Not approximately. Exactly. A specific photon cannot wake up one morning and decide to carry a little extra energy. The amount is fixed from the very beginning. The universe appears remarkably strict about this, and the deeper physicists investigate it, the stranger the situation became. Light was originally understood as a wave. That idea worked incredibly well. Waves can explain reflection, refraction, interference, and diffraction. Many of the most beautiful behaviors of light. But when scientists began examining energy more carefully, they discovered that light behaved as though its energy arrived in packets, not a smooth stream, not a continuous flow. Packets, individual chunks, photons. This was one of the most shocking discoveries in the history of science, because it meant a photon's energy could not be anything whatsoever. Only specific amounts were allowed. The universe was behaving less like flowing water and more like a machine operating in precise steps. The higher the frequency of the light, the more energy each photon carried. The lower the frequency, the less energy. This relationship turned out to be one of the most important discoveries in modern physics, because it revealed that energy and light were connected much more deeply than anyone had imagined. A photon is not simply carrying energy. Its frequency determines the energy it carries. Change the frequency and you change the energy. Change the energy and you change the frequency. The two are inseparable. This is why sunlight contains many colors, different photons carrying different energies. This is why stars can appear red, yellow, blue, or white. This is why ultraviolet light can damage cells more easily than visible light. This is why X-rays can pass through parts of the body that ordinary light cannot. The energy of a photon determines how it interacts with the universe. In many ways, energy is the photon's identity. Yet this only pushes the mystery one step further back. We now understand that photons can carry different amounts of energy. We understand that their frequency determines how much energy they have. But we still haven't answered the original question. Where does that energy actually come from? If a blue photon carries more energy than a red photon, something must have supplied that extra energy before the photon ever began its journey. Nature does not give energy away for free. Every photon arrives carrying a precise amount, which means somewhere before the photon was born, that exact amount of energy already existed. And that is where the real story begins. There is a simple rule that appears everywhere in physics. Energy cannot simply appear. If energy shows up somewhere, it must have come from somewhere else. That idea is so fundamental that modern physics is built around it. Imagine throwing a ball into the air. The ball gains energy as it rises, but that energy did not come from nowhere. Your muscles supplied it. Your muscles obtained it from food. The food obtained it from plants. The plants obtained it from sunlight. The sunlight came from the sun. Follow the chain far enough, and every piece of energy has a history. Every piece of energy came from somewhere. Photons are no exception. A photon may seem mysterious because it appears suddenly. One moment it doesn't exist, the next moment it does. But the energy it carries must already have existed before the photon was born. The photon is not creating energy. It is receiving energy, carrying energy, transporting energy. This distinction is extremely important because many people unconsciously imagine photons as tiny generators, tiny objects that somehow contain energy inside themselves, as though the photon creates the energy it carries. But that is not what happens. Imagine receiving a package from a delivery driver. The driver did not create the package. The driver simply transported it. In many ways, photons behave similarly. They are nature's delivery system. Their job is to move energy from one place to another, and they do this extraordinarily well. A photon can carry energy across a room, across a planet, across a solar system, across an entire galaxy, sometimes across the observable universe itself. Yet no matter how far it travels, the energy originated somewhere else. This immediately raises a fascinating question. What kinds of things create the energy that photons carry? The answer is surprisingly broad. Almost everything. A campfire emits photons. A light bulb emits photons. A laser emits photons. Stars emit photons. Even your own body emits photons. The process is happening continuously all around us. Every glowing object in the universe is constantly converting other forms of energy into photons. A fire converts chemical energy into light. A light bulb converts electrical energy into light. A star converts energy from nuclear reactions into light. The details differ. The principle remains the same. The photon is never the original source. It is the messenger. Imagine holding a flashlight. When you switch it on, photons begin streaming outward. Thousands of billions of them every second. At first glance, it appears that the flashlight is creating light from nothing. But that isn't true. The battery contains stored energy. That energy is converted into electrical energy. The electrical energy eventually becomes photons. The energy changes form. The photon simply becomes the latest carrier. This idea becomes even more impressive when we look at the sun. Every second, the sun releases an astonishing amount of energy, far beyond anything humanity could produce. An enormous flood of photons leaves its surface every moment. Those photons spread in all directions. Some eventually reach Earth. Others continue into interstellar space. Others may travel for billions of years before encountering anything at all. Yet every one of them carries energy that existed before the photon itself existed. The energy came first. The photon came second. In a way, this reverses how many people instinctively think about light. We often imagine the photon as the important thing, the particle, the traveler, the visible object. But from the perspective of energy, the photon is almost secondary. The energy is the real story. The photon is simply the method nature uses to transport it. This realization reveals something profound. Photons are not merely particles moving through space. They are moving pieces of the universe's energy budget, tiny couriers carrying energy from one location to another. And the universe appears obsessed with keeping track of every transfer. Nothing is lost. Nothing is created from nothing. The accounting always balances. Whenever a photon appears carrying energy, something else must possess less energy than before. A payment has occurred. A transfer has taken place. A transaction has been completed. The photon is the receipt. This brings us back to the question that has been quietly hiding beneath the entire discussion. If photons only transport energy, then what is the original source? Where did the energy inside a photon of sunlight exist before the photon was created? The answer ultimately leads us deep into the heart of stars, because long before sunlight reaches Earth, long before a photon leaves the surface of the sun, long before the photon even exists, a much stranger process is already unfolding in the stellar core. When you look at sunlight, it feels immediate. The light touches your skin, warms a sidewalk, illuminates a room, powers a solar panel. The experience feels simple. A photon leaves the sun and arrives at Earth about 8 minutes later. End of story. But that story is missing almost everything, because the photon's journey does not begin when it leaves the sun. In many cases, the energy it carries has been trapped inside the star for an astonishing length of time. Thousands of years, sometimes hundreds of thousands of years. The photon reaching Earth today may be carrying energy that began its journey long before human civilization built its first cities. To understand why, we need to travel deep into the sun itself, far beneath the glowing surface, far beneath the layers visible through a telescope, all the way into the core. The core of the sun is an environment unlike anything found on Earth. Temperatures exceed 15 million degrees Celsius. Matter exists under extraordinary pressure. Hydrogen atoms are packed together so densely that entirely new physical processes become possible. In this inferno, tiny particles move at incredible speeds. Collisions occur constantly, and occasionally, something remarkable happens. Hydrogen begins transforming into helium. This process is known as nuclear fusion. It is the engine of the sun, the source of almost everything that makes life on Earth possible. Without fusion, the sun would go dark. Without the sun, Earth would become a frozen world drifting through space. Every tree, every ocean, every cloud, every living thing ultimately depends on what happens inside this stellar furnace. Yet fusion itself introduces another mystery, because when physicists first examined the process carefully, they discovered something unexpected. The helium produced at the end weighs slightly less than the hydrogen that went into the reaction. Not much less, just a tiny amount. But the difference is real. A small amount of mass has vanished. At first glance, this seems impossible. Matter cannot simply disappear. So where did it go? The answer was one of the greatest discoveries in scientific history. The missing mass became energy. Einstein revealed that mass and energy are deeply connected. They are not completely different things. They are different forms of the same underlying reality. A tiny amount of mass can become an enormous amount of energy. Inside the sun, this conversion happens continuously. Every second, millions of tons of matter are transformed, not destroyed, converted. The resulting energy begins an extraordinarily long journey outward. This is the point where many people imagine photons being created and immediately flying into space. But reality is much stranger. The interior of the sun is incredibly dense. A photon created near the core cannot simply fly straight outward. There are too many particles in the way, too many atoms, too many collisions. The photon travels a short distance. Then it is absorbed. A new photon is emitted. That photon travels. Then it is absorbed again. Another is emitted. Again and again. Over and over. A chaotic chain of interactions unfolds. The energy slowly works its way outward, not in a straight line, not even remotely. If you could somehow track the path, it would resemble a drunk person wandering randomly through a crowded city. A step one way, a step another, back and forth endlessly. The distance from the core to the surface of the sun is only about 700,000 kilometers. Light could cross that distance in a matter of seconds. Yet because of this endless sequence of absorptions and emissions, the energy may require tens of thousands or even hundreds of thousands of years to finally reach the surface. That fact alone is astonishing. The sunlight touching your face today may contain energy that began its journey long before recorded history, long before the Roman Empire, long before the pyramids were ancient. The photon itself is not that old. The photon reaching Earth probably came into existence much later. but the energy it carries may have spent ages migrating through the star before finally escaping. And when it does escape, something beautiful happens. For the first time, the energy is free, no longer trapped inside the dense interior, no longer endlessly scattered. A photon emerges from the solar surface and enters space. Now the journey becomes easy. The vacuum between the sun and Earth is almost empty. There are very few particles to interrupt the photon, very few obstacles, very few opportunities for interaction. The photon simply travels, minute after minute, million kilometer after million kilometer, until eventually some of those photons arrive here. Some strike the atmosphere, some bounce off clouds, some warm the oceans, some power photosynthesis, some enter your eyes and become vision itself. This is what makes photons so extraordinary. They connect vastly different scales of reality. A nuclear reaction in the core of a star eventually becomes a beam of sunlight on your skin. A tiny conversion of mass deep inside the sun eventually becomes a sunrise. The energy survives the entire journey. It changes form, it changes location, but it never appears from nowhere, and it never travels without a history. Every photon of sunlight carries evidence of events that occurred deep within a star. It is a messenger from an environment we can never directly visit, a tiny piece of stellar history crossing space. Yet this still leaves one important question unanswered. We now know where the energy comes from. We know it ultimately originates in the processes powering stars. But something even stranger remains. If photons are carrying energy away from the sun every second, why doesn't the sun eventually run out? Every second, the sun releases an almost unimaginable amount of energy. The number is so large that it becomes difficult to visualize. In a single second, the sun emits more energy than humanity has used throughout its entire history. And it does this continuously, second after second, minute after minute, year after year, for billions of years. This naturally leads to an unsettling question. How is that possible? If photons are constantly carrying energy away from the sun, shouldn't the sun eventually run out? After all, this is what happens to almost everything we know. A battery drains, a candle burns out, a tank of fuel empties, a fire eventually dies. Whenever energy leaves a system, we expect the system to weaken. Yet the sun has been shining for approximately 4.5 billion years, long before Earth had complex life, long before dinosaurs, long before oceans contained anything resembling humans. The sun was already flooding space with photons, and remarkably, it still has enough energy to continue shining for billions of years into the future. The reason lies in the scale of stars. Human intuition struggles with stars because nothing in everyday life prepares us for objects this large. The sun contains approximately 99.8% of all the mass in the solar system. Every planet combined represents only a tiny fraction of what the sun contains. Jupiter, Saturn, Earth, Mars, everything. Together they are little more than leftovers compared to the star at the center. The sun is not simply large, it is overwhelmingly large, and hidden within that enormous mass is an enormous reserve of potential energy. Deep in the core, hydrogen nuclei are continuously being fused into helium. Every second, billions upon billions of nuclear reactions occur. Each reaction converts a tiny amount of mass into energy. Individually, the amount is small. Collectively, it becomes extraordinary. This is what allows the sun to keep producing photons. The process is not free. The sun is paying a price. Every photon leaving the sun represents energy that the star will never get back. Every beam of sunlight carries away a tiny fraction of the sun's total energy budget. The sun is slowly losing mass because of it. This sounds dramatic, yet the scale once again changes everything. The sun loses roughly 4 million tons of mass every second through the conversion of mass into energy. At first glance, that sounds catastrophic. 4 million tons per second. Surely nothing could survive such a loss. But the sun contains roughly 2 billion tons of matter. Compared to the total mass of the star, 4 million tons is almost nothing. The loss is real, but the reserve is enormous. It is like removing a single grain of sand from a mountain. The mountain does not notice. This is why stars can shine for such long periods. Their energy source is not a chemical reaction like fire. It is a nuclear process tapping into a far deeper reservoir. Chemical reactions rearrange electrons. Nuclear reactions rearrange the nucleus itself. The difference in available energy is staggering. If the sun relied on ordinary combustion, it would have exhausted its fuel long before life appeared on Earth. The fact that stars shine for billions of years was actually one of the great mysteries before nuclear physics existed. Scientists could calculate how much energy the sun emitted, but no known chemical process could explain it. The numbers simply didn't work. The sun should have gone dark millions of years ago, yet geology and biology showed that Earth had existed for much longer. Something was missing. The answer arrived only when humanity discovered the true power hidden inside matter. Mass itself could become energy. The famous equation revealed that even tiny amounts of mass contain extraordinary amounts of energy. Suddenly the puzzle was solved. Stars were not giant fires. They were giant nuclear engines, and every photon leaving a star represents a tiny piece of that transformation. In a sense, photons are carrying away fragments of stellar mass, not chunks of matter, not particles of the sun itself, but energy that ultimately originated from matter deep within the stellar core. This creates a fascinating perspective. The sunlight reaching Earth is not merely light. It is evidence that the sun is slowly changing, slowly evolving, slowly spending part of its enormous reserve. Every sunrise represents another day in the life of a star, another day in which mass becomes energy, another day in which photons begin journeys across space. One day, far in the future, the sun's hydrogen supply will begin running low. The balance inside the core will change. The star will evolve. Its structure will transform. Its future will unfold according to the laws governing stellar evolution. But that future remains unimaginably distant. Human civilization is young compared to the lifespan of a star. All of recorded history occupies only a tiny fraction of the sun's existence. For now, the flow of photons continues. The star remains stable. The nuclear reactions continue. The energy keeps moving outward, and countless new photons begin their journeys every second. Yet hidden within those photons lies another mystery, because although the sun creates photons carrying enormous amounts of energy, not all photons are born equal. Some carry far more energy than others. Some emerge as visible light. Others emerge as ultraviolet radiation. Others as X-rays. The question is no longer where the energy comes from. We now know the answer to that. The deeper mystery is why nature divides that energy into different photons in the first place. Why does one photon carry a little energy while another carries vastly more? And what determines that amount at the exact moment the photon is born? Imagine standing outside on a clear day. The sunlight reaching your eyes contains an enormous range of photons. Some are red, some are orange, some are yellow, some are green, some are blue. Some carry even more energy than visible light and arrive as ultraviolet radiation. Others possess less energy and exist as infrared light. The sun is producing an extraordinary variety of photons. Yet this raises a fundamental question. Why? If all photons are the same kind of particle, why don't they all carry the same amount of energy? Why does nature create so many different versions? The answer begins with one of the strangest facts about reality. The universe does not care about our human categories. To us, red and blue are colors. To nature, they are energy differences, nothing more. When physicists examine light, they are not really studying color. They are studying energy. The colors we see are simply how our brains interpret different photon energies. In a sense, color is a translation, a way for the human nervous system to experience differences in energy. This means that when you look at a rainbow, you are actually looking at a map of different photon energies. The red region contains lower energy photons. The blue region contains higher energy photons. The violet region contains even more. A rainbow is not merely a display of colors. It is a display of energy. And hidden inside that display is an important clue. The energy of a photon is connected to something called frequency. Imagine a wave moving across the ocean. Some waves arrive slowly, others arrive rapidly. The faster the oscillation, the higher the frequency. Light behaves similarly. Although photons are particles, they are also connected to the wave-like nature of electromagnetic radiation. A low-frequency wave corresponds to a lower-energy photon. A high-frequency wave corresponds to a higher-energy photon. This relationship is one of the deepest discoveries in modern physics, because it reveals that energy is not randomly assigned. Nature follows a precise rule. Increase the frequency, increase the energy. Decrease the frequency, decrease the energy. The two quantities are inseparable. This immediately creates a fascinating picture. A red photon is not a weaker version of a blue photon. A blue photon is not a faster version of a red photon. They are both photons. They both move at the speed of light. The difference lies entirely in the amount of energy they carry, and that energy is tied directly to their frequency. The universe seems to prefer this arrangement. Instead of changing the speed of photons, nature changes their frequency. The speed remains fixed. The energy changes. This is completely different from how most objects behave. A car gains energy by moving faster. A baseball gains energy by moving faster. A spacecraft gains energy by moving faster. Photons cannot do that. Their speed is already fixed by the structure of space-time itself. So nature needed another way to distinguish high-energy photons from low-energy photons. Frequency became the answer. The result is a universe filled with different kinds of light: radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, gamma rays. At first, these appear to be different phenomena, different forms of radiation, different categories, but they are all manifestations of the same thing: photons carrying different amounts of energy. The entire electromagnetic spectrum is essentially a giant energy scale. At one end are photons carrying relatively little energy. At the other end are photons carrying enormous amounts. And everywhere in between lies a continuous range of possibilities. This realization explains many of the behaviors we observe around us. Infrared photons can warm your skin. Visible photons allow vision. Ultraviolet photons can damage DNA. X-rays can pass through soft tissue. Gamma rays can penetrate matter with extraordinary power. The photon remains the same fundamental particle. Only the energy changes. And that energy determines how the photon interacts with the universe. In many ways, a photon's energy is its personality. It determines what the photon can do, what it can affect, how it behaves, how matter responds when it arrives. Yet this still leaves an important mystery unresolved. We understand that different photons carry different energies. We understand that frequency determines that energy, but we still have not explained how nature decides the exact value at the moment a photon is created. Why this energy instead of another? Why a red photon instead of a blue one? Why an X-ray instead of visible light? Somewhere, before the photon is born, something determines that outcome. Something decides how much energy the photon will carry. And that decision turns out to be one of the most important processes occurring throughout the universe. Imagine watching two photons being born. One emerges carrying the energy of red light. The other emerges carrying the energy of an X-ray. Both are photons. Both move at the speed of light. Both obey the same laws of physics. Yet one carries vastly more energy than the other. The difference is enormous. A single X-ray photon can carry thousands of times more energy than a photon of visible light. A gamma ray photon can carry millions of times more. Some of the highest energy photons ever detected possess more energy than a baseball moving at highway speeds. Not because they are larger, not because they are faster, but because the amount of energy concentrated within a single photon can become astonishingly large. This raises an unavoidable question. Who decides? What determines the exact amount of energy a photon receives when it comes into existence? At first glance, it almost feels as though nature is making a choice, as though some hidden mechanism is assigning values. This photon gets a little energy. That photon gets a lot. But physics tends to dislike explanations involving choices. Instead, it looks for rules. And the deeper scientists investigated, the more they discovered that photons do not choose their energy. Their energy is determined by the process that creates them. Imagine filling glasses with water. A small glass receives a small amount. A large glass receives a larger amount. The amount inside depends on the container. Similarly, the energy carried by a photon depends on the event that produced it. The photon is not deciding how much energy to take. The process itself determines the amount. This idea appears everywhere in nature. A candle flame produces photons carrying certain energies. A hot stove produces photons carrying different energies. The sun produces an enormous range of photon energies. A medical X-ray machine produces much higher energy photons. A radioactive nucleus may produce higher energy photons still. Every source creates photons according to the energy available within the process itself. In other words, photons inherit their energy. They are born carrying whatever amount the underlying event allows. The photon is more like a messenger than a creator. The message already exists. The photon simply carries it away. One of the most fascinating examples comes from temperature. Imagine heating a piece of metal. At first, nothing unusual happens. The metal becomes warmer, then hotter. Eventually, it begins glowing red. Increase the temperature further, and the glow becomes orange, then yellow, then nearly white. The color changes because the energies of the emitted photons are changing. Higher temperatures tend to produce higher energy photons. This means temperature itself influences the energy of light. A cooler object emits mostly lower energy photons. A hotter object emits higher energy photons. The same basic laws explain why stars have different colors. A red star is generally cooler than a blue star. A blue star is hotter than a yellow star like our sun. The color is revealing information about the average energy of the photons being emitted. In a sense, every beam of light contains clues about its origin. The photons are carrying evidence about temperatures, about physical processes, about conditions at the place where they were born. This is one reason astronomers love light so much. Almost everything we know about the universe comes from photons. We cannot visit distant stars. We cannot travel to remote galaxies. We cannot touch black holes. Yet photons arrive from these places carrying information. Their energy tells stories about environments that may be billions of light years away. A single photon can reveal astonishing details about the universe, where it came from, how energetic its source was, what happened during its journey, even how fast distant galaxies are moving. The more physicists studied photons, the more they realized something remarkable. A photon is never just a particle. It is also information. Every photon arrives carrying a record of something that happened somewhere else. Its energy is part of that record. Its frequency is part of that record. Its existence is evidence that some physical process occurred. This perspective transforms the original question. Instead of asking where a photon gets its energy, we begin asking what story that energy is telling, because every photon is a messenger, and every messenger has an origin. But there is still a mystery hiding in plain sight. We have talked about photons being born with energy. We have talked about processes transferring energy into photons. Yet one question remains strangely unanswered. What happens after the photon is created? Does it carry exactly the same energy forever? Or can the universe somehow change a photon's energy after it has already begun its journey? For most of this story, the answer has seemed straightforward. A photon receives energy when it is created. Then it carries that energy through space. Simple. At least, that is what many people assume. But the universe is rarely that simple. Imagine a photon leaving a distant galaxy, not a nearby galaxy. A galaxy so far away that its light will spend billions of years crossing the universe before reaching Earth. The photon begins its journey carrying a precise amount of energy. Its frequency is fixed. Its identity is fixed. Its energy has already been determined by the process that created it. Now imagine waiting. A year passes, then 1,000,000 years, then 100 million, then 1 billion. Eventually the photon arrives. Astronomers detect it. They measure its energy. and something strange appears. The photon is carrying less energy than expected. At first glance, this seems impossible. Where did the energy go? The photon did not collide with anything. It did not stop for fuel. It did not hit a cloud of gas. It spent most of its existence traveling through nearly empty space. So how can it arrive with less energy than when it left? This question puzzled physicists for decades because it appeared to challenge everything they knew about light. After all, one of the most remarkable things about photons is their ability to travel enormous distances. A photon can cross the vacuum of space with extraordinary reliability. Unlike a moving object on Earth, it experiences no friction. Nothing gradually slows it down. Nothing wears it out. If a photon leaves the sun, it arrives at Earth carrying essentially the same energy it possessed when it departed. So why should photons from distant galaxies behave differently? The answer turns out to involve something far stranger than the photon itself. The answer involves space. Most people imagine space as an empty stage, a giant arena in which galaxies move around, planets orbit stars, light travels from one place to another. In this picture, space itself remains unchanged, static, passive, motionless. But modern cosmology revealed something astonishing. Space is not static. Space is expanding. Every moment, the universe grows larger. Galaxies drift farther apart. The distances between enormous cosmic structures increase. Not because everything is flying through space, but because space itself is stretching. This idea is difficult to visualize because nothing in everyday life behaves quite like it. Imagine drawing dots on the surface of a balloon. Now, begin inflating the balloon. The dots move apart. Not because they are crawling across the surface. The surface itself is expanding. The universe behaves in a surprisingly similar way, and photons are forced to travel through this expanding reality. This creates a remarkable consequence. As space stretches, the wavelength of the light stretches with it. The photon continues moving at the speed of light. That never changes, but its wavelength becomes longer. And longer wavelengths correspond to lower energies. The photon arrives carrying less energy than before. This phenomenon is known as redshift, and it is one of the most important discoveries in modern astronomy. Light that begins its journey as blue may arrive looking slightly redder. Light that begins as visible radiation may eventually arrive as infrared. The energy gradually decreases as the universe expands. At first, this seems deeply unsettling. Energy cannot simply disappear. We have spent the entire video discussing that principle. Every photon receives energy from somewhere. Every transfer has a source. Every gain has a cost. So what happened here? Where did the missing energy go? Surprisingly, this question does not have a completely satisfying answer. Not because physicists have ignored it, because the universe itself is more subtle than we once believed. The familiar conservation of energy works beautifully in many situations. Inside laboratories, inside stars, inside atoms, throughout most of physics. But on the scale of the entire expanding universe, the concept becomes more complicated. The universe is not a static container. The stage itself is changing. And when space-time changes, some of our intuitive ideas about energy begin behaving in unexpected ways. This realization was shocking. For centuries, energy conservation had seemed almost sacred, one of the most reliable principles in science. Then cosmology revealed situations where reality becomes far more nuanced. The photon did not make a mistake. The equations did not fail. The universe simply turned out to be stranger than expected. And yet there is something beautiful hidden within this story. Because the very fact that photons lose energy through cosmic expansion allows us to measure the universe itself. Astronomers observe distant galaxies. They examine the energies of incoming photons. They compare those energies to what should have been emitted. The difference reveals how much the universe has expanded during the photon's journey. In other words, photons become cosmic historians. Their energies contain records of the changing universe. Every redshifted photon carries evidence that space has stretched, evidence that the cosmos is evolving, evidence that reality today is not exactly the same as reality billions of years ago. The photon arrives as a messenger, and hidden within its energy is a story about the history of the universe itself. This transforms the original question once again. A photon's energy is not merely something it carries, it is information. Information about its origin, information about its journey, information about the structure of reality. And perhaps nowhere is this more apparent than in the oldest photons we have ever discovered. Photons that have been traveling almost since the beginning of time itself. Most photons have relatively ordinary stories. A photon leaves the sun and reaches Earth 8 minutes later. A photon leaves a distant star and arrives years later. A photon bounces off a wall and enters your eye a fraction of a second afterward. These journeys seem impressive to us because human lives are short, but compared to the age of the universe, they are brief. There are photons traveling through space right now that have been moving for almost the entire history of the cosmos. Photons so old that they began their journey before stars existed, before galaxies existed, before planets existed, before anything recognizable existed at all. These ancient travelers are known as the cosmic microwave background, and their existence tells one of the most remarkable stories in all of science. To understand why, imagine rewinding the universe, not thousands of years, not millions, not billions, all the way back to the beginning. As we move backward through time, galaxies become closer together. Clusters of galaxies become compressed. Eventually, everything becomes hotter and denser. The further back we go, the more extreme conditions become. In the early universe, temperatures were so high that atoms could not exist. Matter existed as an intensely hot plasma. Electrons and atomic nuclei moved independently. Photons constantly collided with charged particles. Light could not travel freely. Every direction was blocked. Every photon scattered almost immediately. The universe was essentially opaque, like the interior of a dense fog. Imagine standing inside a cloud so thick that you cannot see even a few centimeters ahead. Light exists, but it cannot travel far. The early universe behaved similarly. Photons were everywhere, yet none could move freely. Then something extraordinary happened. The universe expanded. As it expanded, it cooled. Temperatures gradually dropped. Eventually, a critical threshold was crossed. For the first time, electrons began combining with atomic nuclei to form stable atoms. Suddenly, there were far fewer charged particles available to scatter light. The cosmic fog began to clear. The universe became transparent. And at that moment, an enormous number of photons were released. Not created, released. Freed from a prison they had occupied since the earliest moments of cosmic history. For the first time, light could travel vast distances without constantly being interrupted. Many of those photons are still traveling today, right now, at this very moment. They fill every region of space. They pass through your body continuously. They pass through Earth, through the atmosphere, through entire galaxies. They are everywhere. In fact, there are more of these ancient photons around you than photons coming from stars. Most people never realize this. We tend to think of starlight as the dominant form of light in the universe, yet the cosmos is flooded with ancient radiation left over from its earliest observable era. The reason we do not see it is simple. Over billions of years, the expansion of the universe stretched these photons dramatically. Remember the redshift we discussed earlier. As space expands, wavelengths become longer, frequencies become lower, energies become smaller. The oldest photons have been stretched for nearly 14 billion years. Their energies have dropped enormously. They no longer appear as visible light. They no longer resemble the energetic photons that once filled the young universe. Today, they exist primarily as microwaves, weak, cold, ancient, yet still carrying information. This is what makes them so valuable. These photons are messengers from a time long before stars, long before galaxies, long before the Earth. Every one of them carries a tiny piece of history. When scientists study the cosmic microwave background, they are essentially looking at the oldest light that can ever be observed. Not because older photons do not exist, but because earlier photons were trapped in the opaque plasma of the young universe. This radiation marks the moment when the universe first became transparent, the moment when light finally gained the freedom to travel. And hidden within these photons is an astonishing amount of information. Tiny variations in their energies reveal details about the early universe, differences measured to incredible precision, patterns so subtle that they would be impossible to notice without advanced instruments. Yet from these patterns, scientists have learned extraordinary things: the age of the universe, its composition, its geometry, its evolution, all encoded within the energies of ancient photons. Think about how remarkable that is. A photon carrying a tiny amount of energy arrives at a detector on Earth. Scientists measure it, and from that measurement, they learn something about events that occurred nearly 14 billion years ago. The photon becomes a time capsule, a message sent across almost the entire history of existence. And perhaps this reveals the deepest truth about a photon's energy. The energy is never just energy. It is information. Information about where the photon came from. Information about what happened during its journey. Information about the state of the universe itself. A photon's energy tells a story, and the oldest photons tell the oldest story we can ever hope to hear. But after following photons from stars, through galaxies, across expanding space, and back toward the beginning of cosmic history, one final question remains. A question that is even deeper than where a photon gets its energy. What is energy itself? Because throughout this entire journey, we have treated energy as something familiar, something obvious, something understood. Yet, if we stop and examine it closely, energy may be one of the most mysterious concepts in all of physics. Throughout this journey, we have followed a single question. Where does a photon get its energy? The answer led us through stars, through nuclear fusion, through expanding space, through the oldest light in the universe. Again and again, we followed the trail backward. Every time we found energy, we found something that came before it. A photon received energy from a physical process. That process received energy from another process. That process received energy from something else. The chain continued. And hidden inside that chain was an assumption we rarely question. The assumption that we know what energy actually is. Yet do we? Imagine asking someone what matter is. They might point to a rock, a tree, a planet, their own body. The examples are easy to find. Energy is different. You cannot hold energy in your hand. You cannot look at a pile of energy sitting on a table. You cannot point a telescope at pure energy and observe it directly. Instead, we always encounter energy through its effects. A moving object, a warm object, a beam of light, a stretched spring, a charged battery. Something happens, something changes, and we say energy is involved. This has led physicists to a strange conclusion. Energy may not be a substance at all. It may not be a thing in the ordinary sense. Instead, energy appears to be a property, a number, a quantity that describes the capacity for change. This idea feels almost disappointing at first. After spending an entire video discussing energy, we naturally want a concrete answer. We want to know what energy is made of. We want to imagine it as some hidden material flowing through the universe. But modern physics offers a more subtle picture. Energy is not like water flowing through pipes. It is more like a bookkeeping system, embedded within reality itself. Whenever something changes, energy helps describe the change. Whenever something moves, interacts, heats up, cools down, emits light, absorbs light, or transforms in any way, energy helps track what is happening. In a sense, energy is one of the universe's accounting tools. And remarkably, the accounting always seems to balance. This fact astonished generations of physicists. No matter how complicated a process becomes, energy never appears from nowhere and never vanishes into nothing. It changes form, it changes location, it changes carriers, but the total remains consistent. A moving object can become heat. Heat can become light. Light can become electricity. Electricity can become motion. The forms change endlessly. The accounting survives. This is why the story of a photon's energy is ultimately larger than photons themselves. The photon is simply one participant in an immense cosmic network of energy transfers. The energy inside sunlight may eventually become chemical energy inside a plant. That chemical energy may become food. The food may become motion. The motion may become heat. The heat may eventually leave Earth as infrared photons and return to space. The energy keeps moving, changing form, changing carriers, flowing through reality in an endless sequence of transformations. In this sense, the universe resembles a vast web of energy exchanges. Stars release energy, planets absorb it, life temporarily organizes it, light transports it, matter stores it. Physics describes the rules governing its movement. Yet the deeper we look, the stranger the concept becomes. Because energy appears everywhere, it explains an enormous portion of what happens in nature, and yet it remains surprisingly abstract. Richard Feynman, one of the greatest physicists of the 20th century, once pointed out something fascinating about energy. We know how to calculate it. We know how to measure it. We know how it behaves. But explaining what it fundamentally is remains surprisingly difficult. In many ways, energy resembles space and time. We use these concepts constantly. We build entire theories around them. Yet when someone asks what they truly are, the answers become much less clear. The closer we approach the foundations of reality, the more familiar concepts begin to feel mysterious. And perhaps nowhere is that mystery more apparent than in a photon. A photon seems simple, a tiny particle of light crossing space, yet following the story of its energy reveals an extraordinary chain of connections. A photon leads us to atoms. Atoms lead us to stars. Stars lead us to nuclear fusion. Fusion leads us to mass itself. Mass leads us to the deepest structures of physical law. A simple beam of light becomes a doorway into the foundations of reality. And perhaps that is the most remarkable part of all. The next time sunlight enters a room, it may appear ordinary, a patch of brightness on a wall, a reflection in a window, a warm ray of light crossing the floor. But hidden inside that light is a history stretching back through the universe, a history of energy transfers, a history of physical processes, a history that may have begun thousands, millions, or even billions of years before the photon reached you. The photon did not create its energy. It inherited it, carried it, protected it across unimaginable distances, and ultimately delivered it to a new destination, a tiny messenger carrying a piece of the universe's story. And in doing so, it reminds us of something profound. Even the simplest things in nature are often connected to mysteries far larger than they first appear. A photon seems simple until you ask where its energy comes from. Then suddenly, an entire universe unfolds behind the question. As we come to the end of this journey, it is worth returning to the question that started it all. Where does a photon get its energy from? At first, the answer seemed simple. Perhaps the energy came from the photon itself. Perhaps it somehow carried its own supply. Perhaps the mystery would disappear once we looked closely enough. Instead, the question led us much deeper. We discovered that every photon is part of a much larger story, a story stretching through stars, through matter, through the expansion of the universe itself, a story in which energy is constantly changing form, constantly moving, constantly being passed from one part of reality to another. The photon is not the source, it is the messenger, a tiny traveler carrying a piece of cosmic history across space. And perhaps that is what makes light so extraordinary. Every beam of sunlight that reaches Earth began as part of a chain of events stretching far beyond our everyday experience. Every photon arriving in your eye carries evidence that something happened somewhere else. Something changed. Something transferred energy. Something left a trace that survived the journey. In that sense, light is much more than illumination. It is communication, a way for distant parts of the universe to reach across space and tell us their story. The stars tell their story through light. Galaxies tell their story through light. Even the early universe tells its story through light. And all we have to do is listen. The next time you see sunlight passing through a window or watch the colors of a sunset spread across the sky, remember that you are looking at energy that has traveled an incredible path to reach you. Energy with a history. Energy that existed long before the photon itself was born. And perhaps that is one of the most beautiful ideas in all of physics. Nothing exists in isolation. Every photon is connected to something larger. Every piece of energy is part of a story. And every question, no matter how simple it seems, can reveal an entire universe hiding beneath the surface. Thank you for joining me on this journey through one of the deepest mysteries of light. If you enjoyed this exploration, consider subscribing to Science Sleep Theory for more calm journeys into the hidden questions of physics, cosmology, and reality itself. Until next time, keep wondering. And as the universe continues to fill the darkness with countless streams of ancient light, allow yourself to rest, knowing that even the smallest photon carries a story billions of years in the making.